Welcome to this explainer. Today we're unpacking the incredibly strict environmental guidelines that keep our sterile medicine safe from contamination. When we talk about pharmaceutical manufacturing, the stakes literally could not be higher. The difference between a safe, life-saving injection and a really dangerous one often comes down to invisible particles floating in the air of the manufacturing facility. So, we're going to look closely at the precise area classifications for typical process stages and the heavy-duty design considerations you absolutely have to have in these different grades of environments.
Okay, let's dive right into this by asking what sounds like a deceptively simple question, just to wrap our heads around the massive scale of microbial defense we're actually talking about here. How clean is a clean room? Well, when we use the word clean in everyday life, we usually just mean, free of visible dirt. But in sterile manufacturing, we are fighting an entirely invisible enemy. We're engineering spaces to control microscopic airborne particles and microorganisms to an almost impossibly precise degree. It is this wild, fascinating intersection of architecture, thermodynamics, and microbiology.
Here is our roadmap for today. We'll start by defining clean areas, then we'll break down the 4 GMP grades, map out manufacturing processes to those grades, look at how we design for them, and finally, take a walk through the core journey of a facility.
Let's jump right into Section 1, Defining Clean Areas. This is the absolute foundation of sterile manufacturing.
Right off the bat, there's a very clear, very important distinction between a general clean area and a critical area. A clean area is essentially any room that is specifically designed and controlled to prevent particle and microbial contamination. It consistently meets a specific baseline of air cleanliness. But a critical area? That is the ultimate inner sanctum of our operation. This is the highly specialized zone where sterilized drug products, the containers and the closures are actively exposed to the environment. If contamination happens here, it's game over. It goes straight into the patient's medicine.
Moving on to Section 2, the 4 GMP grades. This is where we see environmental control escalate to some pretty extreme levels. We classify these environments into 4 progressively stricter grades: A, B, C, and D. And what's really interesting is that we measure them in 2 different states. We check them at rest, meaning the equipment is all set up but nobody is in the room working, and in operation, meaning the room is live and people are actively working inside. Grade A is the gold standard. It rigidly maintains an ISO 5 standard both at rest and in operation. To put that into perspective, that means a maximum of just 3,520 particles, specifically those 0.5 micrometers or larger, per cubic meter of air. Compare that to a grade C room in operation, which allows over 3.5 million of those exact same particles. So grade A allows absolutely no drop in air quality, no matter what activity is happening inside.
And that brings us to this absolutely crucial number: less than 1. This is the microbiological limit. Less than 1 colony-forming unit, or CFU, is allowed in a grade A zone, period. Whether we're actively sampling the air, leaving settle plates out for hours, swabbing surfaces, or even testing the operator's gloves, the limit is strictly less than 1. It represents near-perfect sterility. Just as a quick comparison, a grade D room allows up to 200 CFUs in a sample. So the jump from D to A, it is a monumental shift in cleanliness.
All right, Section 3, Mapping Processes to Grades. Now we need to figure out where specific operations are actually legally permitted to happen.
The regulatory guidelines basically divide manufacturing into 2 massive buckets. On one side, we have terminally sterilized products. This means you prepare the medicine, put it in its container, seal it up tight, and then the entire finished product is sterilized, usually by blasting it with intense heat. Because you have that final kill step at the very end, the preparation work can happen in less critical grade C or D areas. But on the flip side, we have aseptic processing. This is for products that would be destroyed by that intense final heat. So every single component, the drug, the vial, the stopper, has to be sterilized completely separately and then carefully assembled in a perfectly sterile environment. It's incredibly high risk, so it absolutely requires grade A zones wrapped in grade B or C backgrounds.
When you look at the exact operations, you can see how this risk mapping plays out in reality. Something like aseptic compounding or formulation, that might happen in a grade C environment. But think about filling and stoppering open vials. The product is totally, completely exposed to the air. Because of that, the actual filling has to take place inside a local grade A zone. But remember, a grade A zone doesn't just float in the middle of a regular room. It needs a highly controlled grade B background room physically wrapped around it as a buffer. The level of risk dictates the strictness of the grade.
Okay, Section 4, Designing for the grade. Let's talk about how architecture and HVAC systems act as a totally active defense system.
You can think of the HVAC system as the lungs of the facility. The minimum air changes per hour escalate incredibly fast as you move up the grades. In a Class D area, the air in the room is completely scrubbed and replaced 20 times every single hour. But watch what happens as we move to a Class B environment, the background for our critical core. In Class B, that air is fully changed 65 times per hour. It's wild. This rapid turnover, pushing air through massive HEPA filters, literally flushes contamination right out of the room before it ever has a chance to settle. And in the Grade A zone itself, the air isn't just swapped out. It's delivered in a continuous, unidirectional flow at a very specific velocity, 0.45 meters per second, to physically wash over and protect the product.
But hey, it's not just about airflow. The design of these spaces heavily targets the human element, mostly through really tight temperature and humidity controls. For example, in an ISO 8 or Grade D process room, the temperature is strictly held between 19 and 25 degrees Celsius, with relative humidity between 40 and 55%. Why so strict? Well, first, it prevents microbial growth, because microbes love heat and moisture. But the second reason is for the operators. Humans are by far the biggest source of contamination in a clean room. If an operator starts sweating inside their specialized gown, they shed massively more particles. The physical architecture backs this up too. Rooms are built with smooth, hard surfaces and seamless rounded floor-to-wall junctions. Dirt literally has nowhere to hide, and cleaning becomes effortless.
Finally, Section 5, the core journey. Let's actually trace the movement through a facility's defense layers.
This step-by-step movement perfectly illustrates a concept called defense in depth. You cannot simply open a door from a regular hallway and stroll into a Grade A zone. No way. It is a very deliberate journey through cascading levels of cleanliness. You start in an unclassified corridor, step into a Grade D passage. From there, you move through a specialized Grade C airlock, which acts like a pressure bubble to stop any dirty air from rushing in behind you. Then, you step into a Grade B changing room where operators undergo intense, rigorous gowning to cover literally every inch of skin. Only after all of that do you reach the Grade A aseptic zone. It is a series of tightly controlled concentric protective rings.
Ultimately, the entire goal of all these classifications, which is heavily emphasized by this regulatory mandate, is the physical protection of the sterile product. This is exactly why we're seeing a massive shift towards using isolator systems, carefully engineered curtains, and heavy rigid plastic shields right there within the Grade A zones. Think of it like this. The room protects the local zone, and the local zone's equipment protects the drug itself.
So, I'm going to leave you with this final thought. When we look at these strict engineering guidelines, are we just building rooms, or are we really engineering an invisible machine designed to keep global medicine safe? We aren't just slopping up drywall and plugging in some air conditioners here. By perfectly balancing air velocity, particle counts, microbial limits, and spatial geometry, we are literally engineering a continuous, living machine. And its sole purpose is to guarantee that when a patient receives a sterile medicine, it is exactly that, perfectly, unequivocally sterile. Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you in the next one.